Just before 9.2b, how did you guys do with calculating average atomic mass? That was review from the summer. It was assigned 2 days ago. Thumbs up, thumbs down, thumbs in the middle, or I don't know because I didn't do it. Okay, where are we at? Are we thumbs up? Are we thumbs down? Are we thumbs in the middle? Please hold up your thumb high so I can see it because I'm short and I need to be able to see it. Okay, most of us are thumbs up. All right, so we're going to, if you were not thumbs up, if you're like, then please do come see me at Flex. We're now going to look at finding the percent abundance of 2 different isotopes. You can do it for 3 isotopes, but then you have to be given one of the percentages, okay? So instead of asking you for the average atomic mass, it will say, what is the percent abundance of this isotope and what is the percent abundance of that isotope? Are we okay with the term percent abundance? Percent abundance just means what percentage is isotope A and what percentage is isotope B. What are isotopes? Tell your partner, what are isotopes? Okay, so isotopes. Different what of the same element? Versions of the same element that have different numbers of what? Neutrons. Neutrons, and because they have different numbers of neutrons, they therefore have different mass numbers. Not atomic masses. Because remember, the atomic mass is the average of all naturally occurring isotopes. Yes, so the number on the periodic table is not the mass number. The number on the periodic table is the average of all the mass numbers. Yes? So if we were to look at carbon, carbon comes in several versions. It comes in carbon with a mass number of 12, carbon with a mass number of 13, and carbon with a mass number of 14. However, on the periodic table, the average mass of carbon is given as 12.01. So what does that tell you? It tells you that most carbon atoms have a mass of we have carbon 12, we have carbon 13, we have carbon 14. Those are their mass numbers. The atomic mass is it 12.01? I'm pretty sure it's 12.01. Just double check. Yeah, 12.01. What does that tell you about the relative abundance? Relative abundance means how much do you have of one version compared with the other versions? Pardon me? You have a lot of which one? Do you have a lot of carbon 12? Do you have a lot of carbon 13? Do you have a lot of carbon 14? Do you have 50-50? Do you have 33-33-33? Which one is the most abundant? Carbon 12, because the average is closest to 12, right? How much carbon 13 and 14 will there be?
Very little.
Very little, okay? So we're like, okay, that's good. Now, let's say we had chlorine, which comes in two versions, 35, and chlorine 37, and the atomic mass is 35.5. And if I said to you, what is the relative abundance? So which one is present in greater quantities? Which one is present in lesser quantities? That's relative. How do they compare to each other? There is relatively more. Which one? 35. Yeah, because if you were to take the average of those two, if it was 50-50, like if you just said, okay, I'm going to take the average, assume it's 50-50, I would get 35, or sorry, I would get 36. Yes, but I don't. I get a number closer to 35. So there is more, and there is less. Those are their relative abundances. And for carbon, it was mostly carbon 12. So what we're going to do today is we're going to be not just saying this one has more, this one has less. We're going to actually be finding the actual percentages. Okay? So we're going to say, based on the average atomic mass, and where would we find the average atomic mass? That is on the periodic table. So just look it up. You are going to define the decimal percent of each isotope. Now, you're only going to have two isotopes. If you have three isotopes, you cannot solve it this way because you'll end up with one equation and two variables. And can you solve one equation with two variables? No. So we want one equation with one variable. Yes? So we can only do this with two systems. So 100%, remember, as a decimal, oh, periodic table. And it actually says it down on the next line. Go find it on the periodic table. Okay? 100% as a decimal is how much? 1. Okay, so if you only have 2 isotopes, then the 2 percentages have to add up to 100, and the 2 decimal percentages have to add up to 1. So if we let X equal the decimal percent of isotope A, and if we let 1 minus X then would be whatever the other one is, yes? 100% minus whatever percent isotope A was. That's going to be a percent of isotope B. And if we add those two together, we will get the average atomic mass, okay? Actually, that's not true. I'm sorry. It's more complicated than that. Get rid of that. Blah. Okay. If we take our percent, mass of A times our percent of A, which is X, and then we have the mass of B times the percent, which is isotope B, which is 1 minus X. Yeah? And you add those together, then you will get the mass of the element. Okay, this is the average atomic mass. Does this look like the same formula that you used to find the average atomic mass? Let's go back and look. Finding the average atomic mass, you said, oh, hey, we have a percent of isotope A and the mass of isotope A. So this is the percent of A, and this is the mass of A. Yeah? This is on page 40. So these were the ones that you mostly said you had thumbs up on, okay? So percent of A times mass of A, and then we have percent of isotope B times the mass of isotope B and then what do we do with those two numbers to get our overall atomic mass? We add them, yes, and we get our average atomic mass. So guess what? We took the percent of A times the mass of A, and we added it to the percent, which was isotope B, and multiplied it by the mass of B. So far, so good. And when we added those together, we got the average atomic mass. Is good? So in the problems that you've done previously in the summer and a couple days ago, you were given all of these numbers and asked to find the average atomic mass. Yeah? Now we are giving you the average atomic mass and saying, please find the percentages. You'll be given mass A, you'll be given mass B, you'll be given the average atomic mass, and you have to find the percent A and the percent B. And the percent A, that's going to be X, and the percent B is going to be 1 minus X. Is this seeming familiar now? A little bit? Okay. So we go back to here. Okay. Determine the relative abundance of unknown isotope by solving for X. Determine the percent. Since they're decimal percents, you just multiply by 100 to get a percentage. So here we have an example. We are given we want the relative abundance of the isotopes if the masses of one isotope, we have nitrogen 14, which has a mass of 14.003 AMU. And we have nitrogen, this is back on page 43. We have our second isotope, which is nitrogen 15, mass of 15.000 AMU. And we have the average atomic mass of the two together. We go on to a fancy periodic table with a lot of decimal places, and we get 14.007. Yes, your periodic table only goes to 14.0. If you use the AP one, it goes to 14.00. But we're using a fancy one that goes to many, many decimal places to find the average atomic mass. So for nitrogen 14, we know that its mass is 14.03. We know for nitrogen 15, its mass is 15. We don't know our percentages, so we have to say, okay, X is going to be the percent of nitrogen 14. That means that 1 minus X is the percent of nitrogen 15. And it doesn't matter whether you write it, you could write it as X times mass of A plus 1 minus X times mass of B. Or you could write it this way, it doesn't matter. But I like putting the X second because then I end up with my mass of A, which is 14.03. Right? And then I have my X after it. We have our mass of B, which is 15.00. And that's 1 minus X. And then you just do some algebra. Algebra, 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 algebra. La, 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 la. X is equal to 0.996. Make sure you can chug through the algebra when you do the examples, okay? There's 3 sig figs due to subtraction. Let's see how that works here. We have a subtraction here. And when we do a subtraction, what do we go to? We go to the first uncertain digit. Who is the first uncertain digit in 14.007? 7. How about in 15.000? The last 0. That is in the thousandths position. So our uncertain digit is in the thousandths position. Okay, thousandths position. Which means how many sig figs do we have in our final number? 3 sig figs. Yeah? And that means when we're done, we can only have 3 sig figs. So there we go, and we get 0.996. Let's go back and look at what did we define X as being. X was the decimal percent of nitrogen 14. Okay, decimal percent of nitrogen 14 was X. And that means that the percent of nitrogen 14 is equal to 99.6%. What does that mean for our percent, which is nitrogen 15? What is the percent which is nitrogen 15? 0.4%. And so then you could say the abundance of the nitrogen 14 isotope is 99.6%, and the abundance of the nitrogen 15 isotope is 0.4%. Okay, so it's just kind of about wrapping your head around the math here. There's nothing different in this next example other than the fact that we haven't been given those fancy numbers. Yes? We haven't been given the 14. We haven't been given any special number for chlorine 35, like not 35.004 or whatever the heck it is. We haven't been given that. So we can only work with 35. For chlorine 37, we can only work with the number 37 because we don't have any other information, but we would do it the same way. Chlorine 35, the mass is 35 AMU. And we're going to let X equal its decimal percent. 37 has a mass of 37 AMU, and we're going to let 1 minus X equal its decimal percent. Throw everything into the formula. We have the mass of A times the decimal percent of A. Oh, please don't do that. And then we have the mass of B times the decimal percent of B. And that's equal to our average atomic mass. Plug in 35 for the mass of A. Plug in 37 for the mass of B. Algebra, 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 algebra. You end up with X is equal to 0.775. However, if we look at our sig figs, our uncertain digit is in the ones position, yes? So we would have it in the ones position. But I'm not going to round off until I get to the end. So this would then become 1.0. This becomes kind of a stupid problem. So I feel like, right? It's like, oh, it's 100% chlorine 35, which it obviously isn't. So probably you would not get something like this and be expected to do something with sig figs. Do you know what I mean? Percent abundances and sig figs can get messy. Yeah? But most of the time, we give you lots of digits to work with. So for example, our first one, antimony 123, is 122.904. So you've got lots of sig figs, yes? Would you like a couple moments to do exercise 1? Okay, give exercise 1 a try. And if you finish exercise 1, you can try exercise 2.